Welcome to Dreamy Facts. As the day gently recedes, we invite you to settle into a space of calm contemplation. Tonight, we embark on a journey through the fascinating world of aviation, exploring approximately 100 facts that reveal intricate patterns, subtle wisdom, and profound ingenuity embedded within humanity's quest for flight. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or retention. We will observe the intricate dance of engineering and courage, the subtle adaptations of design, and the quiet wisdom embedded in the very act of soaring above the earth. Each fact is a small window into the vast and interconnected tapestry of aviation, from its earliest glimmers to its most modern marvels, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. We will trace the evolution of wings, the whispers of wind through early fabrics, and the roar of engines that brought distant lands closer. This journey is one of quiet appreciation, a gentle descent into the marvels of human innovation and the enduring dream of flight. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations. And we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. As we begin our exploration, we turn our gaze to the dawn of flight, a period marked by audacious dreams, relentless experimentation, and the quiet dedication of pioneers. This chapter invites us to appreciate the foundational moments and the often overlooked figures who laid the groundwork for the skies we navigate today. Let us gently uncover the initial steps that transformed an ancient human aspiration into a tangible reality. The Wright brothers' lesser-known innovations. While Orville and Wilbur Wright are universally celebrated for the first sustained controlled flight, many of their less famous contributions were equally critical. Historians generally agree that their most significant innovation was not simply the airplane itself, but their sophisticated understanding and application of three-axis control, pitch, roll, and yaw. This control system, which allowed a pilot to manipulate the aircraft's attitude in all three dimensions, was a radical departure from the inherent instability of earlier designs and remains fundamental to aircraft control even today. Furthermore, the brothers meticulously conducted their own wind tunnel experiments, a pioneering approach that allowed them to develop more efficient wing shapes and propeller designs than had previously been achieved. Their initial calculations based on existing data proved inaccurate, leading them to question established theories and conduct their own rigorous data-driven research. This scientific methodology, rather than pure trial and error, set them apart. They also designed and built their own lightweight gasoline engine, a crucial component since no suitable commercial engines existed at the time that met their specific power-to-weight ratio requirements. Their commitment to solving each engineering challenge systematically established a new paradigm for aeronautical development. Early female aviators and their records. The early days of aviation were not solely the domain of men. Courageous women also took to the skies, often breaking barriers and setting remarkable records. Harriet Quimby, an American journalist and film screenwriter, became the first woman to earn a pilot's license in the United States in 1911. Just a year later, in 1912, she achieved another historic feat by becoming the first woman to fly solo across the English Channel. A perilous journey that demonstrated both skill and immense bravery. Across the Atlantic, Raymonde de la Roche of France had already become the first woman in the world to pilot a plane in 1908, and subsequently the first to earn a pilot's license in 1910. Her achievements, including setting an altitude record, inspired many. Bessie Coleman, an African-American woman, faced racial and gender discrimination in the US, leading her to travel to France to learn to fly. In 1921, she became the first African-American and first Native American woman to hold a pilot's license, performing daring aerial stunts and advocating for aviation among her community. These women, among others, not only proved their capabilities in a male-dominated field, but also pushed the boundaries of what was considered possible in the nascent age of flight, contributing significantly to the public's perception and acceptance of aviation. The first commercial flights and their challenges. The transition from experimental flight to commercial aviation was a gradual process, fraught with significant challenges. While the earliest flights were often for mail delivery or military reconnaissance. The first scheduled passenger air service in the United States began on January 1st, 1914, connecting St. Petersburg and Tampa, Florida. This service, operated by the St. Petersburg-Tampa airboat line, used a Ben West 14 flying boat and carried a single passenger per trip. The fare for the 23-minute, 18-mile journey was $5, which was a substantial sum at the time, equivalent to several $100s today. Early commercial flights faced numerous obstacles, including rudimentary navigation systems, unreliable engines, and the absence of established air traffic control. Weather conditions posed a constant threat, and comfort for passengers was minimal, often involving open cockpits and loud, vibrating engines. Furthermore, public trust in air travel was low, as crashes were relatively common and often fatal. The limited range and payload capacity of early aircraft also restricted the viability of longer routes. Despite these difficulties, these pioneering efforts demonstrated the potential of air travel to shrink distances and transform transportation, laying the groundwork for the global network we experience today. Pioneers of flight beyond the Wrights. While the Wright brothers secured their place in history, it is important to acknowledge that many other inventors around the world were simultaneously pursuing the dream of flight, often achieving significant, though sometimes less recognized milestones. Gustav Whitehead, a German immigrant to the United States, is claimed by some historians and researchers to have achieved powered flight in 1901, 2 years before the Wrights, though photographic and eyewitness evidence remains highly debated and lacks the definitive corroboration of the Wrights' achievements. Alberto Santos Dumont, a Brazilian aviator living in France, made significant contributions to dirigible design and achieved the first public flight of a heavier-than-air aircraft in Europe in 1906, generating immense public excitement. His 14 bis biplane, while less advanced than the Wright Flyer in terms of control, was a crucial step in European aviation. Samuel Langley, an American astronomer and physicist, also experimented extensively with powered flight through his Aerodrome series, though his full-scale manned attempts failed spectacularly. Even Clément Ader, a French inventor, claimed to have made a short, uncontrolled hop in a steam-powered bat-winged monoplane called the Iole as early as 1890. These diverse efforts highlight a global fascination with flight and the simultaneous, often independent development of similar technologies across different continents. The role of photography in early aviation. Photography played a dual and critical role in the advancement of early aviation, serving both as a scientific tool for documentation and a powerful medium for public engagement. Early aviators, including the Wright brothers, extensively used still photography to document their experiments, analyze flight characteristics, and record their successes, providing irrefutable evidence of their achievements. These photographs were crucial for verifying claims and for studying aerodynamic principles. Beyond scientific documentation, aerial photography quickly became a new frontier. The first photograph taken from an aircraft was captured by French photographer and balloonist Gaspard Félix Tournechon, known as Nadar, from a tethered balloon over Paris in 1858. However, it was only a few years after the Wrights' first flight that photography from powered aircraft became feasible. These early aerial images offered unprecedented perspectives of landscapes, proving invaluable for mapping, reconnaissance, and later urban planning. The public, captivated by the novelty of flight, was also eager to see images of these flying machines and the world from above. Photographs of daring aviators and their machines helped to popularize aviation, generating excitement and attracting investment, thereby fostering its rapid development from a niche pursuit to a global phenomenon. Early aircraft materials and construction. The materials and construction techniques of early aircraft were remarkably simple, reflecting the nascent understanding of aerodynamics and structural integrity. The first successful aircraft, such as the Wright Flyer, were primarily constructed from spruce wood, a lightweight yet strong timber, often reinforced with wire bracing for rigidity. The wings and control surfaces were typically covered with treated cotton fabric, such as unbleached muslin or, quote, one-coated linen, which was stretched taut and painted to provide an aerodynamic surface and protect against moisture. This fabric, once coated with a cellulose nitrate lacquer, dope, would shrink, tightening the covering and adding structural integrity. Fasteners primarily consisted of nuts, bolts, and screws, with piano wire often used for tension bracing. The engines, custom built by the aviators themselves or adapted from automobile designs, were usually made of cast iron or aluminum alloys, balancing power output with weight. While rudimentary by modern standards, these materials and methods required immense craftsmanship and ingenuity. The engineers of the era had to innovate with limited resources, often relying on empirical testing and a keen understanding of mechanical principles to ensure their creations could withstand the stresses of flight, pushing the boundaries of what was possible with available technology. As the day gently recedes, painting the sky with the softest hues of twilight, we invite you to settle deeper into your quiet space. We have journeyed through the audacious beginnings of flight, marveling at the first tentative leaps and the ingenuity of those who dared to dream. Now, as the evening deepens, casting a serene glow upon our shared exploration, we turn our gaze to a period of unprecedented acceleration, a time when the nascent wings of aviation were forced to grow at an astonishing pace, transforming from a curiosity into a formidable force. This chapter, like a calm breeze carrying whispers of history, will reveal how necessity, daring, and relentless innovation propelled aviation forward, shaping its destiny in ways both profound and unexpected. The early 20th century, a time of both grand ambition and burgeoning global tensions, saw the quiet wonder of flight rapidly evolve. What began as a scientific pursuit and a spectacle for the masses soon found itself thrust into a role no one had fully anticipated. The outbreak of World War I in 1914 dramatically altered the trajectory of aviation, transforming flimsy contraptions into sophisticated machines, and pilots from adventurous sportsmen into courageous combatants. Before the Great War, aircraft were largely perceived as experimental novelties, their practical applications still largely undefined. However, the static trench warfare that characterized much of the conflict quickly revealed the immense strategic value of aerial observation. Suddenly, the ability to see beyond enemy lines, to map troop movements, identify artillery positions, and photograph defensive structures became invaluable. This immediate demand for reconnaissance pushed aircraft development at an astonishing rate. What began with pilots simply carrying maps and binoculars quickly evolved into sophisticated aerial photography, with cameras mounted directly onto the aircraft. The need to protect these vital reconnaissance missions, and conversely, to deny the enemy similar intelligence, gave birth to aerial combat. This period saw a rapid iteration of designs as engineers frantically worked to improve speed, altitude, endurance, and armament. The war, though tragic, acted as an unparalleled catalyst, compressing decades of potential peacetime development into just a few intense years, solidifying aviation's place as a critical component of modern warfare and, by extension, modern life. The very fabric of aviation changed under this pressure. Manufacturers, previously small workshops, scaled up to mass production. Pilots, once a handful of enthusiasts, were now trained in their thousands, developing new skills and tactics in the unforgiving skies above the battlefields. The gentle hum of experimental engines gave way to the urgent roar of squadrons, and the solitary flight of a pioneer was replaced by the intricate dance of aerial formations. This period, though fraught with danger and loss, laid much of the groundwork for the future of aviation, forcing incredible leaps in engine reliability, airframe strength, and aerodynamic understanding. As reconnaissance planes became crucial, so too did the imperative to either protect one's own or shoot down the enemy's. Early attempts at aerial combat were rudimentary, involving pilots firing pistols or rifles at each other, or even throwing bricks and grappling hooks. Such desperate measures quickly highlighted the need for purpose-built aerial weaponry. The most significant breakthrough arrived with the development of the .2, a revolutionary invention that allowed a machine gun to fire through the propeller arc without striking the blades. While various inventors contributed to this concept, the German engineer Antony Fokker perfected a reliable version in 1915, equipping it onto the Fokker Eindecker monoplane. This invention was a game changer. Suddenly a pilot could aim their entire aircraft at the enemy, a much more intuitive and effective method than trying to aim a separate weapon. The Fokker-Eindecker, with its synchronized machine gun, gave Germany a period of air superiority known as the Quote 3, demonstrating the profound impact of technological innovation in aerial warfare. This led to a frantic arms race, as Allied nations scrambled to develop their own synchronized firing mechanisms and superior fighter aircraft, such as the Sopwith Camel and the SPAD-S-13. These early fighter planes, often biplanes, were agile and deadly, piloted by courageous individuals who became known as Quote 4 for their multiple victories. Their daring dogfights, a ballet of death high above the trenches, captivated the public imagination and forged the legend of the combat pilot. This era not only established the concept of air-to-air combat, but also pushed the boundaries of aircraft maneuverability and pilot skill to unprecedented levels. Even amidst the turmoil of war, the practical utility of aviation began to extend beyond military applications. The ability to traverse distances at speeds previously unimaginable held immense civilian potential, particularly for the swift delivery of communication. The concept of Quote 5 emerged as a powerful force, not only proving the reliability and speed of aircraft, but also driving significant advancements in navigation, infrastructure, and public acceptance. While passenger service was still in its infancy, the urgency and value of mail delivery made airmail an ideal proving ground for aviation's commercial potential. The United States Post Office Department, seeing the promise, established its first regular airmail service on May 15, 1918, between Washington, D.C., Philadelphia, and New York City. Initially, this service was operated by Army pilots and aircraft, but it soon transitioned to civilian control, marking a crucial step towards independent commercial aviation. The success of these early routes, despite significant challenges, demonstrated that aircraft could operate on a schedule, carry a useful payload, and offer a significant speed advantage over traditional ground and rail transport. Airmail was not just about speed, it was about reliability. To maintain schedules, planes had to fly in varying weather conditions over diverse terrain, and often at night. This demand pushed manufacturers to build more robust and dependable aircraft. It also spurred the development of ground infrastructure, including dedicated airfields, maintenance facilities, and rudimentary weather reporting systems. The public, initially skeptical of air travel, began to witness the tangible benefits of aviation as letters and packages arrived faster than ever before. This practical application helped to normalize flight, transitioning it from a daredevil stunt to a vital public service. The success of airmail services across the globe, from the US to Europe and beyond, provided the economic impetus and operational experience necessary for the eventual expansion of commercial passenger airlines. The brave men and women who flew the early airmail routes were truly pioneers, pushing the boundaries of human endurance and ingenuity. Unlike today's pilots who rely on sophisticated instruments and global positioning systems, these early aviators navigated largely by Quote 6 and visual landmarks. They followed railroad tracks, rivers, and roads, often flying low to identify familiar towns or geographical features. When flying at night, navigation became an even more perilous challenge. Early solutions included bonfires lit along the route, rotating beacons, and even giant arrows painted on barn roofs to point the way. These pilots faced immense dangers: unreliable engines, unpredictable weather, and a complete lack of air traffic control. Forced landings in remote fields were common, and the ability to repair an engine on the spot was often a necessary skill. Despite these formidable obstacles, the airmail pilots achieved remarkable feats, consistently delivering mail and demonstrating the inherent capabilities of aircraft. Their dedication and courage were instrumental in developing the early techniques and technologies that would eventually lead to modern instrument flight and global air navigation systems. They were the unsung heroes who, flight by arduous flight, laid the invisible pathways in the sky, transforming an empty expanse into a network of vital routes. The post-World War I era, often referred to as the incest, quote, 7, saw an explosion of record-breaking attempts. These challenges, driven by a combination of prestige, prize money, and an unyielding human desire to conquer the unknown, spurred incredible advancements in aircraft design, engine performance, and navigational capabilities. They captured the world's imagination, cementing aviation's place in their popular consciousness. Among the most iconic challenges of the Golden Age was the Orteig Prize. In 1919, New York hotelier Raymond Orteig offered $25, zero to the first aviator to fly non-stop from New York to Paris or vice versa. For 8 years, numerous attempts were made, many ending in failure, injury, or death, highlighting the immense difficulty of such a feat. The challenge demanded an aircraft capable of unprecedented range and reliability, and a pilot possessing extraordinary skill, endurance, and courage. It was Charles Lindbergh, a relatively unknown 25-year-old airmail pilot, who ultimately claimed the prize. On May 20th to 21st, 1927, he flew his custom-built single-engine monoplane, the Spirit of St. Louis, non-stop from Roosevelt Field, New York, to Le Bourget Airport, Paris. The flight covered approximately 3,600 miles, 5,800 kilometers, in 33.5 hours. Lindbergh's success was not just a testament to his individual bravery and skill, but also to the meticulous design of his aircraft. To maximize fuel capacity, the Spirit of St. Ian, Louis placed the main fuel tank directly in front of the pilot, forcing Lindbergh to navigate with a periscope and side windows for forward visibility. This design choice, though unconventional, was critical for carrying the necessary fuel load. His solo flight captured the world's imagination, turning him into an instant global hero, and dramatically boosting public confidence in the safety and potential of air travel. It proved that long-distance intercontinental flight was not only possible, but a viable future for transportation, ushering in an era of rapid expansion in commercial aviation. The lessons learned during World War I, coupled with the demands of airmail and record-breaking flights, led to significant advancements in aircraft materials and design. While early aircraft relied heavily on wood, fabric, and wire, the interwar period saw a gradual but decisive shift towards more robust and aerodynamically efficient construction. Metal, particularly aluminum alloys, began to replace wood for fuselage and wing structures. This transition allowed for stronger, lighter, and more durable aircraft that could withstand higher stresses and more adverse weather conditions. The biplane, with its inherent structural strength and maneuverability, dominated early aviation. However, as engine power increased and aerodynamic understanding deepened, the monoplane began to gain prominence. With a single set of wings, monoplanes offered less drag, allowing for greater speed and fuel efficiency, crucial for long-distance flights. Retractable landing gear, enclosed cockpits, and more sophisticated aerodynamic shaping became standard features, further reducing drag and improving performance. Engines became more powerful and reliable, moving from simple rotary designs to more advanced radial and inline configurations. These technological leaps were not merely incremental improvements, they were foundational changes that transformed aircraft from fragile, open cockpit machines into sleek, enclosed vehicles capable of carrying more passengers and cargo over greater distances at higher speeds. This period of intense innovation laid the groundwork for the modern airliners and sophisticated military aircraft we know today, reflecting a relentless pursuit of efficiency, safety, and performance. As we gently conclude this segment of our journey, we hope these facts have painted a vivid picture of aviation's rapid evolution. From the desperate urgency of war to the thrilling challenges of pioneering flights, each step forward was a testament to human ingenuity and an unyielding spirit of adventure. We invite you to let these quiet truths settle, perhaps sparking new wonders as you drift towards a peaceful rest. We eagerly await our next shared moment, ready to continue our exploration into the boundless skies of aviation history. As the gentle hum of the day softly recedes and the last embers of the golden age cast long reflective shadows across the vast canvas of aviation history, we invite you to drift deeper into the serene expanse of human ingenuity. We have witnessed the audacious leaps of early pioneers and the rapid, often brutal, acceleration of flight in times of conflict. Now, we turn our gaze toward a period of profound maturation, where the dream of widespread air travel began to solidify, transforming from a daring spectacle into a tangible reality, and then into an indispensable part of our connected world. Allow your thoughts to gently settle as we explore how the lessons learned and the technologies forged in earlier eras coalesced, giving rise to aircraft capable of greater comfort, reliability, and reach. This segment of our quiet journey through the skies illuminates the intricate dance of engineering prowess, unyielding ambition, and the relentless pursuit of progress that defined aviation's middle years. We will trace the lines of innovation that etched new pathways across the globe, bringing distant lands closer and reshaping our perceptions of time and space. The roaring 20s and 30s, while still celebrating record-breaking flights, also saw the slow, deliberate birth of scheduled commercial passenger service. This was a challenging endeavour, far removed from the romantic solitude of Lindbergh's journey. It required not just reliable aircraft, but also the infrastructure to support them, the regulations to govern them, and the public trust to fill them. Before extensive land-based runways became commonplace, especially for intercontinental travel, the majestic quote 9 reigned supreme. Aircraft like Pan American World Airways' iconic Clippers, the Sikorsky S-42, and later the Boeing 314, offered luxurious, albeit expensive, long-distance travel across oceans. These magnificent machines, often described as floating palaces, were equipped with dining rooms, sleeping berths, and attentive service, making the journey itself a grand adventure. They connected continents, forging early air routes across the Pacific and Atlantic, shrinking the vastness of the world and laying the crucial groundwork for global air networks. We imagine the gentle lapping of waves against their hulls as they awaited departure, a stark contrast to the concrete runways of today. As commercial flights grew longer and more sophisticated, the need for passenger comfort and care became evident. In 1930, Ellen Church, a registered nurse, became the world's first flight attendant, flying for Boeing Air Transport, a predecessor to United Airlines. Her initial role, and that of the early Sky Girls or stewardesses, was multifaceted, assisting passengers, providing medical care, serving meals, and even helping to refuel the aircraft. This pioneering profession not only enhanced the passenger experience, but also helped to foster a sense of safety and refinement, making air travel more appealing to a broader public. We reflect on the profound shift from a purely functional journey to one where comfort and hospitality become integral to the experience. Perhaps no aircraft symbolizes the maturation of commercial aviation more profoundly than the Douglas DC-3. First flown in 1935, this twin-engine propeller plane was a game-changer. It was reliable, relatively fast for its time, and crucially profitable for airlines even without government subsidies. Its robust design and ability to operate from shorter, less developed runways made it ideal for expanding domestic and international routes. During World War II, it was repurposed as the C-47 Skytrain, proving its versatility and durability in countless military operations. After the war, thousands of C-47s were converted back into DC-3s, forming the backbone of global commercial aviation for decades. Even today, a few DC-3s continue to fly, a testament to their exceptional engineering and timeless design. We feel a quiet reverence for this workhorse of the sky, a true marvel of its era. The expansion of commercial routes demanded more than just reliable aircraft. It necessitated advancements that would make flying safer, more predictable and more comfortable for passengers. The challenges of weather, navigation, and human endurance at altitude drove engineers and scientists to push the boundaries of what was possible. Early aircraft flying at lower altitudes subjected passengers to cold, noise, and turbulence. To fly higher, above much of the weather and turbulence, and to achieve greater speed and efficiency, required a fundamental change. The Boeing 307 Stratoliner, first flown in 1938, was the first commercial airliner with a pressurized cabin. This revolutionary feature allowed the aircraft to maintain a comfortable cabin altitude, e.g. 8,000 feet, while the plane itself flew much higher, e.g. 20,000 feet or more. This innovation dramatically improved passenger comfort, reducing fatigue and making long-distance travel far more appealing. We envision the silent, serene experience of flying above the clouds, a luxury born of ingenious engineering. In aviation's infancy, pilots navigated primarily by VFR, relying on sight of the ground, landmarks, and clear weather. However, to ensure scheduled service regardless of conditions, IFR became essential. Pioneering work in the 1920s and 30s by figures like Jimmy Doolittle demonstrated that pilots could fly solely by reference to instruments. This led to the development of sophisticated cockpit instrumentation, including artificial horizons, gyroscopic compasses, and altimeters. The ability to fly in clouds or at night without visual reference to the outside world revolutionized aviation, making it a truly all-weather 24-hour mode of transport. We pause to appreciate the trust placed in these delicate instruments, guiding human courage through the unseen. Hand in hand with instrument flight came the development of radio navigation aids. early systems, like the Quote 14, provided pilots with audible signals that indicated their position relative to a ground station. A continuous Quote 15 signal would guide them along specific air routes. Later, more advanced systems like the Very High Frequency Omnidirectional Range, VOR, and the Instrument Landing System, ILS, provided precise directional guidance and vertical glide path information for approaches to runways. These innovations transformed navigation from an art reliant on visual cues and dead reckoning into a precise scientific discipline, vastly improving safety and efficiency. We listen for the faint guiding whispers of these early radio beacons, pulling aircraft through vastness. Just as World War I propelled aviation from novelty to military utility, World War II ignited an unprecedented surge in aeronautical development. The global conflict demanded aircraft that were faster, stronger, could fly higher, carry heavier loads, and navigate with pinpoint accuracy. This era served as a harsh but incredibly effective proving ground for technologies that would define the post-war world. While early jet engine concepts date back to the 1930s, World War II accelerated their practical application. Germany's Heinkel, He-178, which first flew in 1939, was the world's first turbojet-powered aircraft. This was followed by the Messerschmitt Me 262, the first operational jet fighter, which saw combat in 1944. Concurrently, Britain developed its own jet engine, leading to the Gloucester Meteor fighter. The jet engine, with its promise of vastly superior speed and altitude compared to propeller-driven aircraft, heralded a new era in aviation. Its development was a monumental leap, fundamentally altering the trajectory of aircraft design and performance. We marvel at the raw power and elegant simplicity of this revolutionary propulsion system. The invention and rapid development of radar, Quote 16, during World War II had a profound impact on aviation. Initially used for detecting enemy aircraft and ships, radar soon found applications in air navigation and bombing. It allowed pilots to Quote 17 through darkness and clouds, identify targets, and navigate accurately over long distances. Post-war radar evolved into sophisticated air traffic control systems, ground-based navigation aids, and airborne weather radar, dramatically enhancing flight safety and operational efficiency. We consider the unseen waves that now guide and protect, a silent guardian in the skies. The demands of global warfare necessitated aircraft capable of carrying immense payloads over vast distances. Aircraft like the American B-29 Superfortress, a technologically advanced bomber with features like pressurized cabins and remote-controlled gun turrets, pushed the boundaries of size and complexity. Similarly, large transport aircraft became vital for moving troops and materiel. This era saw the refinement of structural design, aerodynamics, and engine technology to support these larger, more capable machines, laying the groundwork for the massive airliners of the future. We feel the sheer scale of these flying giants, a testament to industrial might and engineering ambition. With the cessation of hostilities, the technological leaps of World War II were swiftly adapted for civilian use. The stage was set for the most dramatic transformation in commercial aviation, the transition from piston engines to jets. This change would not merely be an incremental improvement, it would redefine air travel entirely. On July 27, 1949, the British de Havilland Comet took to the skies, becoming the world's first commercial jet airliner. Its sleek design, quiet cabin, and unprecedented speed captivated the public and promised a new era of luxurious swift air travel. Passengers could now fly at altitudes and speeds previously unimaginable, far above the weather, reaching destinations in a fraction of the time. While early models faced tragic structural failures that led to temporary grounding and extensive redesigns, the Comet undeniably pioneered the jet age, proving the viability and immense potential of jet-powered passenger flight. We remember the initial thrill and the painful lessons learned, both crucial for the path ahead. While the Comet blazed the trail, it was the American Boeing 707 and Douglas DC-8, introduced in the late 1950s, that truly commercialized the jet age. These aircraft were larger, faster, and more robust than their predecessors, benefiting from the Comet's lessons in advanced engine technology. They offered unparalleled range and capacity, making transcontinental and intercontinental jet travel a widespread reality. The 707 in particular became an icon of the era, profoundly impacting global commerce, tourism, and culture. These jets transformed the world, shrinking distances and making international travel accessible to millions. We envision the elegant lines of these aircraft, carving paths across the sky, forever altering our perception of distance. The advent of the Boeing 707 and DC-8 marked the definitive end of the piston-engine propeller aircraft's dominance on major long-haul routes. While propeller planes continued to serve regional and short-haul markets, the speed, smoothness, and efficiency of jet travel made them the preferred choice for passenger airlines seeking to offer the best experience. The transition was swift and dramatic, forever changing the soundscape of airports and the experience of flying. The gentle thrum of propellers gave way to the powerful roar of jet engines, symbolizing a new age of speed and efficiency. We reflect on this pivotal moment, where one era gracefully ceded to another, opening up boundless new possibilities. As we gently conclude this segment of our journey, we hope your mind feels a little lighter, your spirit a little more reflective. We have traversed a period of immense growth and transformation, witnessing the quiet determination that turned audacious dreams into the foundations of modern air travel. The sky, once a distant frontier, had become a highway, paved by the brilliance and courage of countless individuals. Take a moment to simply breathe, allowing these wondrous facts to settle within your thoughts. Let the quiet appreciation for human endeavour fill this peaceful space. As the evening deepens, we prepare to explore even grander horizons, where the future of flight continues to unfold with ever-increasing marvels. Rest easy, and let the gentle current of discovery carry you onward. As the roar of the first commercial jetliners, the Boeing 707s and Douglas DC-8s, receded into the annals of history, marking the decisive end of the propeller era for major routes, we find ourselves drifting further into the boundless skies of innovation. The world, once vast and segmented, now felt intimately connected, its distant shores brought within a few hours' reach. Yet, human aspiration, a gentle current always pushing against the known, refused to settle. The quest for speed, for capacity, for ever greater mastery over the elements, continued to beckon, drawing us into new realms of aeronautical marvel. The triumph of the jet engine was not merely about covering distances faster, It ignited a deeper yearning for ultimate speed, a desire to transcend the very sound barrier itself. We invite you to recall a time when this invisible wall was a formidable, even mythical obstacle. For decades, it was believed that approaching the speed of sound would cause an aircraft to break apart, a phenomenon known as compressibility. Yet, the intrepid spirit of aviation pioneers knew no such limits. It was in 1947, a mere 2 years after the close of the Second World War, that this formidable barrier was finally shattered. A quiet, unassuming man named Chuck Yeager, a test pilot of extraordinary courage and skill, strapped himself into the cockpit of the Bell X-1, a rocket-powered aircraft aptly named Glamorous Glennis after his wife. Shaped like a bullet designed with thin, straight wings to resist the forces of compressibility, the X-1 was a testament to audacious engineering. On October 14th, flying high above the Mojave Desert, Yeager pushed the X-1 past Mach 1, the speed of sound, creating a thunderous sonic boom that echoed across the dry lake beds below. This was not just a flight. It was a profound declaration that the sound barrier was penetrable. A scientific and psychological breakthrough that opened the floodgates for supersonic flight. The calm, steady hand of Yeager, combined with the brilliance of the Bell engineers, unveiled a new dimension of speed, forever changing our understanding of what was possible in the air. The breaking of the sound barrier was merely the first step. The dream of commercial supersonic travel soon took hold, promising to shrink the world further still, making transatlantic journeys a matter of mere hours. This ambition culminated in 2 extraordinary aircraft, symbols of Cold War technological rivalry and shared human ingenuity. The Anglo-French Concorde and the Soviet Tupolev Tu-144. The Concorde, with its elegant delta wing and distinctive droop nose, was a masterpiece of design and engineering collaboration between Britain and France. From its first commercial flight in 1976, it offered a truly unparalleled travel experience, whisking passengers across the Atlantic at speeds exceeding Mach 2, twice the speed of sound. Imagine, if you will, departing London or Paris in the morning and arriving in New York before lunch, having gained time as you chase the sun westward. The Concorde was more than a mode of transport. It was a symbol of luxury, prestige, and the pinnacle of aviation technology, a testament to what nations could achieve when united by a common soaring vision. Its cabin, though intimate, offered an experience of serene speed, a quiet hum accompanying the breathtaking acceleration that few could ever forget. Across the Iron Curtain, the Soviet Union pursued its own supersonic dream with the Tu-144, often dubbed the Concordski, due to its striking resemblance to its Western counterpart. While the Tu-144 achieved supersonic flight and entered limited passenger service, it faced significant technical challenges and was ultimately withdrawn from passenger operations, serving primarily as a cargo and research aircraft. Both supersonic giants, despite their technological brilliance, faced formidable economic and environmental hurdles, including immense fuel consumption, the disruptive sonic boom over land, and high operational costs. The Concorde, after decades of iconic service, was eventually retired in 2003, a poignant reminder that even the most advanced machines must yield to the evolving currents of practicality and sustainability, yet their legacy endures. a quiet testament to humanity's relentless pursuit of speed and the courage to push the boundaries of what was once considered impossible. Even as some engineers pursued the zenith of speed, others envisioned a different future. One, the skies were accessible not just to the privileged few, but to millions. The early jetliners had proven the commercial viability of air travel, but they were still relatively small, carrying perhaps 100 passengers. The next great leap was in capacity, a vision that would fundamentally reshape airports, cities, and the very fabric of global tourism. This vision materialized in the form of the Boeing 747, the majestic queen of the skies, which took its first flight in 1969. Born from a bold gamble and the foresight of figures like Joe Sutter, the chief engineer, the 747 was unlike anything seen before. Its distinctive hump housing the cockpit and an upper deck gave it an unmistakable profile. Designed initially for a potential military cargo contract, Boeing adapted it for commercial passenger service, foreseeing a future where air travel would explode. And explode it did. The 747's sheer scale was revolutionary. It could carry over 400 passengers, more than double the capacity of earlier jets. This dramatic increase in seating capacity, combined with its impressive range and efficiency for its time, led to a significant reduction in the cost of air travel. Suddenly, intercontinental flights became an affordable reality for a much wider segment of the population. The 747 transformed airports, requiring longer runways, larger terminals, and more sophisticated ground support equipment. It fostered the growth of international tourism, allowing families to visit distant relatives, adventurers to explore new continents, and businesses to expand globally with unprecedented ease. We recall the quiet awe inspired by seeing such a colossal machine gracefully lift into the sky, a testament to human ingenuity and the intricate dance of physics and engineering. The 747 was not just an airplane. It was a catalyst for globalization, shrinking the world not by speed alone, but by making it universally accessible. Its gentle, steady presence in the skies for over 50 years symbolizes reliability and the enduring dream of flight for all. While fixed-wing aircraft dominated the narrative of speed and long-distance travel, another branch of aviation was quietly yet profoundly evolving, the realm of vertical flight. We invite you to consider the helicopter, a machine that defies the conventional rules of aerodynamics, offering a unique blend of agility and access. Its lineage traces back to early sketches by Leonardo da Vinci, but practical, controlled helicopter flight only became a reality in the mid-20th century. Unlike airplanes, which require forward speed to generate lift over their wings, helicopters achieve both lift and propulsion from rapidly rotating blades or rotors. This allows them to take off and land vertically, hover in place, and even fly backward or sideways, capabilities that fixed-wing aircraft simply cannot match. The pioneering work of designers like Igor Sikorsky, who developed the VS-300 in 1939, laid the foundational principles for modern helicopters, making them practical for a myriad of applications. The versatility of the helicopter quickly became apparent. From daring mountain rescues to critical medical evacuations, from heavy lift construction to military reconnaissance, helicopters carved out indispensable roles. They could access remote locations inaccessible by road or conventional aircraft, making them vital tools in disaster relief, offshore oil operations and law enforcement. We reflect on the calm assurance provided by the distinctive thwack-thwack of rotor blades overhead, often a sound of hope and assistance in dire circumstances. The helicopter, with its unique ability to pause and survey, to rise and descend without a runway, represents a profound expansion of humanity's reach into the three-dimensional world, a quiet testament to the diverse forms that the dream of flight can take. As the number of aircraft in the sky proliferated and their speeds increased, the need for precise control and navigation became paramount. The early days of visual flight rules and rudimentary radio navigation gave way to sophisticated systems designed to manage an increasingly complex ballet of departures, arrivals, and en route traffic. We turn our attention now to the intricate, often unseen, infrastructure that ensures the safe and orderly flow of air travel. The evolution of air traffic control, ATC, is a story of continuous technological advancement. From controllers peering at flight strips and tracking aircraft on basic radar screens, the system matured into a highly integrated network. Secondary surveillance radar, which interrogates aircraft transponders, began to provide controllers with vital information such as altitude, speed, and identification, far beyond what primary radar alone could offer. This allowed for more precise separation of aircraft, preventing collisions and optimizing airspace utilization. The cockpit itself underwent a profound transformation. The traditional array of analog dials and gauges began to be replaced by glass cockpits, where multifunction displays presented integrated flight information, navigation data, and engine parameters. The introduction of Flight Management Systems, FMS, allowed pilots to program entire flight plans, optimizing routes for fuel efficiency, and managing the aircraft's performance with unprecedented precision. Perhaps the most transformative development in navigation was the advent of the Global Positioning System, GPS. Initially developed for military use by the United States, GPS became available for civilian applications, revolutionizing how aircraft navigate. By receiving signals from a constellation of satellites orbiting Earth, an aircraft's onboard receivers could pinpoint its exact location with incredible accuracy, providing continuous, worldwide three-dimensional positioning. This capability enhanced safety, improved efficiency, and enabled more direct routes, saving time and fuel. We observed the quiet confidence that these invisible signals instill, guiding aircraft with serene precision through day and night, through clear skies and turbulent weather, a testament to the elegant integration of space technology into our earthly journey. As the latter half of the 20th century unfolded, another revolutionary concept began to take shape, one that would redefine the very notion of a pilot. We are speaking, of course, of unmanned aerial vehicles, or UAVs, more commonly known today as drones. While rudimentary remote-controlled aircraft existed earlier, the technological advancements of this era, particularly in miniaturization, computing power and communications, truly propelled UAVs into the realm of practical application. Initially developed for military reconnaissance, surveillance, and target acquisition, early drones were often simple, propeller-driven aircraft, remotely piloted from ground stations. They offered the ability to gather intelligence in dangerous environments without risking human lives. Over time, their capabilities expanded dramatically. Advanced sensors, high-resolution cameras, and sophisticated data links transformed them into invaluable tools for a wide array of missions, from monitoring battlefields to inspecting infrastructure. The quiet, almost imperceptible flight of these machines, controlled by an unseen hand potentially thousands of miles away, represented a new frontier in aviation. It challenged traditional perceptions of flight, separating the human operator from the physical presence in the aircraft. This development, though rooted in military necessity, would eventually spill over into countless civilian applications, from delivering packages and surveying crops to capturing breathtaking aerial photography and assisting in search and rescue operations. We contemplate the serene efficiency of these autonomous eyes in the sky, a quiet evolution that continues to reshape our interaction with the aerial domain, promising both profound utility and new ethical considerations as we gently drift into the future. As the sun dips below the horizon, casting long, peaceful shadows, we reflect on these incredible journeys of innovation, from the first tentative supersonic flights to the democratizing power of the jumbo jet, from the versatile dance of the helicopter to the invisible guidance of ATC and the silent vigil of drones. Humanity's aerial aspirations have continued to expand, pushing the boundaries of what is possible. Each advancement, each new machine, represents countless hours of dedication, moments of profound insight, and the unwavering belief that the sky is not a limit, but an invitation. As we prepare to gently close our eyes, we carry with us the quiet wonder of these achievements, a soothing reminder of the enduring power of human ingenuity. As the day gently recedes further into the quiet embrace of night, we continue our shared journey, allowing the whispers of innovation to guide us. We have witnessed the sky transform from an unimaginable frontier into a connected global highway, propelled by audacious dreams and relentless ingenuity. From the earliest, delicate gliders to the intricate dance of modern air traffic control and the emerging omnipresence of unmanned aerial vehicles, humanity's aspiration has known no bounds. Now, as the stars begin to punctuate the deepening indigo canvas above, we invite you to gaze forward, past the present marvels, into the quiet hum of tomorrow's skies, where the future of flight is not merely imagined but meticulously engineered. The profound majesty of flight has always carried a quiet responsibility, and as our understanding of our planet deepens, so too does our commitment to preserving its delicate balance. The next great frontier in aviation is not merely speed or altitude, but sustainability. We are on the precipice of a conscious shift towards a greener horizon, where the roar of engines might one day be replaced by a more gentle, almost silent hum, and the emissions that once marked our passage become but a memory. One of the most promising avenues is the development and widespread adoption of sustainable aviation fuels, SAFs. These remarkable fuels, often derived from agricultural waste, algae, or even captured carbon, offer a vital bridge to a carbon-neutral future. Unlike traditional jet fuel, which extracts fossil carbon from deep within the earth, SAFs utilize carbon that is already part of the active carbon cycle, significantly reducing net emissions. Imagine, if you will, the vast global fleet soaring on fuel born from the very plants that breathe our air, a testament to cyclical harmony and ingenious chemistry. This quiet revolution in fuel technology is not a distant dream but a tangible reality, with increasing numbers of commercial flights already incorporating SAFs, paving a sustainable path forward. Complementing this, the dream of electric and hybrid electric propulsion is taking tangible shape. While fully electric commercial flights for long-haul journeys remain a significant engineering challenge, the horizon for regional travel and urban air mobility is bright, with the promise of silent, emission-free flight. Imagine small, nimble aircraft, perhaps carrying a handful of passengers, lifting off with only the gentle whir of electric motors, powered by advanced batteries or hydrogen fuel cells. These innovations promise to redefine localized air travel, offering a cleaner, quieter presence in our communities and reducing our reliance on fossil fuels. Beyond fuel and propulsion, every contour, every surface of an aircraft is being re-examined through the lens of efficiency, the subtle art of aerodynamic refinement. Now guided by sophisticated computational fluid dynamics, CFD, and biomimicry, allows engineers to sculpt the invisible currents of air with unprecedented precision, coaxing out every ounce of efficiency. We are learning from the silent flight of owls and the effortless glide of albatrosses, translating nature's wisdom into the intricate dance of engineering. This holistic approach, from the energy source to the very shape of the wing, is guiding us towards a future where aviation's footprint is as light and fleeting as a cloud. To achieve these ambitious goals of sustainability and efficiency, the very fabric of our flying machines must evolve. The quiet strength of advanced materials and revolutionary manufacturing processes is dramatically reshaping how aircraft are conceived, built, and maintained. We are shedding the weight of the past, embracing lighter, stronger, and more resilient composites that promise not only enhanced performance, but also greater longevity. The era of advanced composite materials has truly dawned. Carbon fiber composites, once exotic and costly, are now fundamental to modern aircraft design, replacing traditional metals like aluminum in wings, fuselages, and empennages. These materials offer an unparalleled strength-to-weight ratio, allowing for lighter aircraft that consume less fuel and can carry greater payloads. Imagine a fuselage that is not riveted from thousands of metal sheets, but is instead a seamless, flowing structure, meticulously crafted from layers of carbon fiber, each strand imbued with incredible tensile strength. This reduction in weight is a quiet victory for efficiency, enhancing range and reducing operational costs, all while improving structural integrity and resistance to fatigue. Alongside these material breakthroughs, additive manufacturing or 3D printing is revolutionizing the production floor. This technology allows engineers to build complex components layer by delicate layer, much like a potter shapes clay, but with microscopic precision and unparalleled geometric freedom. This means parts can be designed with intricate internal structures that were previously impossible to cast or machine, optimizing strength where needed and removing material where it serves no purpose. The quiet hum of a 3D printer can now create engine components, cabin interior parts, or even structural elements, reducing waste, accelerating production cycles, and opening up entirely new possibilities for customized on-demand parts. This localized manufacturing capability promises a more sustainable and responsive supply chain, further reinforcing the quiet evolution of the industry. Furthermore, the methodologies of design themselves are undergoing a profound transformation. With the advent of AI-driven generative design, algorithms can explore millions of design iterations in a fraction of the time it would take human engineers. These intelligent systems can optimize for a multitude of factors: weight, strength, aerodynamics, and even manufacturability, to achieve unprecedented levels of efficiency and safety. Picture a wing, its shape not merely drawn by human hand, but meticulously evolved by intelligent software, its every curve and surface a testament to computational brilliance, perfectly tuned to the invisible currents of the air. This quiet collaboration between human ingenuity and artificial intelligence is pushing the boundaries of what is aerodynamically possible, creating aircraft that are both beautiful and incredibly efficient. As we continue our gentle journey through the evolving landscape of aviation, the allure of speed remains an eternal beacon. While the Concorde once graced our skies with supersonic elegance, humanity's gaze is now fixed on a new frontier: hypersonic flight. Imagine traversing continents in a mere matter of hours, perhaps even minutes, pushing the boundaries of velocity to speeds exceeding Mach 5. This is not merely an incremental step, but a leap, promising a future where global travel is redefined by ultra-rapid transit. The engineering challenges are immense, demanding breakthroughs in propulsion, materials capable of withstanding extreme thermal loads, and advanced aerodynamic designs that can navigate the delicate interface between atmosphere and the very edge of space. The dream of a hypersonic passenger craft, perhaps whispering across the sky at speeds unimaginable today, remains a quiet but persistent aspiration, a testament to our continuous quest for faster connections across our vast world. Intricately linked to this pursuit of extreme speed is the burgeoning field of commercial suborbital flight. We are witnessing a blurring of the lines between atmospheric flight and space travel, as pioneers venture into the realm where the sky truly meets the cosmos. Companies are now offering journeys to the very edge of space, allowing passengers to experience weightlessness and witness the profound curvature of the Earth against the inky blackness of the cosmos. These aren't orbital missions, but rather brief, exhilarating excursions that climb to altitudes well above the conventional limits of aviation, then gently return. The quiet thrill of seeing Earth from this unique vantage point, a perspective once reserved for a select few astronauts, is now becoming an accessible reality, opening up a new dimension of travel and exploration. It's a peaceful reminder of our planet's beauty and our place within the grand expanse. This convergence of hypersonic and suborbital capabilities suggests a future where the concept of flight itself expands. We may soon see vehicles capable of atmospheric flight for global transport that can also ascend to suborbital altitudes for unique experiences, or even serve as stepping stones for deeper space exploration. This quiet expansion of our aerial domain is a wondrous testament to our enduring ingenuity, pushing the boundaries of what is possible and inviting us to look beyond the immediate horizon. As the stars gleam with a gentle intensity, let us turn our gaze closer to home, to the very cities where many of us reside. The dream of personal flight, once confined to science fiction, is poised to usher in a quiet revolution in urban air mobility, UAM. Imagine a future where traffic congestion on our roads is eased by a network of small, electric vertical takeoff and landing, eVTOL, aircraft, gracefully ferrying passengers across urban landscapes. These air taxis or personal air vehicles promise to add a new dimension to intra-city travel, transforming daily commutes and offering unprecedented connectivity. The concept is simple yet profound. Small, highly automated aircraft capable of lifting off and landing vertically, eliminating the need for long runways and allowing for direct point-to-point travel within metropolitan areas. The design of these eVTOLs often incorporates multiple small rotors, powered by electric batteries, designed for quiet operation and enhanced safety through redundancy. Picture a serene evening where you might step onto a designated vertiport atop a building, and within minutes be gently lifted into the sky, soaring above the bustling streets below, reaching your destination swiftly and calmly. Of course, the realization of such a vision presents its own set of fascinating challenges. Creating an intricate ballet of aerial vehicles within dense urban environments demands incredibly robust air traffic management systems, far more complex than those overseeing traditional airports. Issues of quiet operation, safety standards, public acceptance, and the necessary infrastructure, the vertiports, charging stations, and maintenance hubs, are all being meticulously addressed by engineers, urban planners, and regulators. Yet the promise remains compelling, a future where the sky above our cities becomes a quiet, efficient thoroughfare, decongesting ground transportation and offering a peaceful, elevated perspective on our daily lives. This quiet revolution holds the potential to profoundly reshape our urban experience, making our cities more connected and our journeys more serene. In our contemplative journey through aviation's future, we arrive at a point where the very essence of piloting is being redefined. The deepening symbiosis between human and machine, driven by BEM, artificial intelligence, AER, and the march towards greater autonomy. Building upon the glass cockpits and sophisticated flight management systems we explored earlier, AI is now poised to become an even more integrated, intelligent co-pilot, enhancing safety, efficiency, and the overall experience of flight. Imagine an aircraft where AI assists not just with navigation, but with every facet of the flight, from dynamic flight planning that optimizes routes in real time based on weather and air traffic, to predictive maintenance systems that alert ground crews to potential issues before they arise. AI is transforming operational paradigms. It can process vast amounts of data instantaneously, offering real-time decision support to human pilots, anticipating potential hazards, and even suggesting optimal responses in complex scenarios. This intelligent oversight creates an unprecedented layer of safety and efficiency, allowing human pilots to focus on strategic decision-making and the subtle nuances of flight, while the machine handles the intricate data processing. The conversation naturally extends to fully autonomous flights. While human pilots remain central to commercial passenger aviation, the quiet evolution of autonomy is already visible in cargo operations and the increasing sophistication of unmanned aerial vehicles. We might foresee a future where cargo planes operate with minimal or even no human crew on board, guided by advanced AI systems, navigating global routes with tireless precision. The ethical and safety considerations are profound, but the technological progress is undeniable. This quiet shift raises fundamental questions about the role of the human in the cockpit, not as a replacement but as an evolution, where human oversight, strategy, and the profound wisdom gained from countless hours aloft remain paramount. The pilot's role may shift from manual control to a more supervisory and strategic one, but the human element, the ultimate decision-maker, will remain central to the gentle journey through the skies. As our tranquil exploration of aviation's future gently draws to a close, and the quiet embrace of night deepens around us, we are reminded that at the heart of every technological marvel, every audacious leap, lies the fundamental human desire to transcend the earth. From the earliest whispers of Icarus's wings to the hypersonic dreams of tomorrow, the sky remains an eternal muse, beckoning us upwards. We have traversed a wondrous path together, from the fragile wings of the pioneers to the intricate dance of modern flight and the visionary concepts that will shape our future. This journey through 100 aviation facts you didn't know is more than a collection of details. It is a celebration of human ingenuity, persistence, and the serene beauty of aspiration. Now, as your mind gently settles, filled with the echoes of engines and the silent grace of flight, we invite you to carry these quiet wonders into your dreams. May the gentle hum of innovation and the peaceful spirit of exploration accompany you as you drift into a calm and restorative rest. The sky, in all its boundless majesty, awaits your return to its quiet contemplation. As the day gently recedes, painting the western sky with hues of lavender and deep indigo, we invite you to settle deeper into this tranquil space. The whispers of the wind outside your window seem to carry not just the sounds of the fading light, but also the murmurs of a future yet unwritten, a symphony of human aspiration continuing its unending melody. Our journey through the annals of aviation has brought us to the very precipice of tomorrow, where the audacious dreams of yesterday are giving way to the profound innovations of the coming age. We now turn our contemplative gaze toward the unresolved mysteries, the grand challenges that beckon the brightest minds, promising a future of flight that is both wondrous and profoundly responsible. The roar of the jet engine, a sound synonymous with power and speed, has long defined our aerial journeys. Yet, as our collective consciousness awakens to the delicate balance of our planet, the quest for truly sustainable aviation has become not merely an ambition, but an imperative. We observe a quiet revolution unfolding, an intricate dance between engineering prowess and ecological mindfulness, designed to reconcile our desire for flight with our duty to the earth. At the heart of this transformation lies the fervent development of sustainable aviation fuels, SAFs. Imagine a future where the fuel powering our mighty airliners is no longer drawn from ancient reserves, but is instead synthesized from agricultural waste, municipal solid waste, used cooking oil, or even captured carbon dioxide. This is not a distant fantasy, but a tangible reality being meticulously crafted in laboratories and refineries across the globe. We find that SAFs, chemically identical to traditional jet fuel, can reduce life cycle carbon emissions by up to 80% or more, offering an immediate and impactful pathway to decarbonisation. The challenge, however, is immense, scaling production to meet the colossal demands of global air travel, ensuring these fuels are economically viable and their feedstock sources truly sustainable, without competing with food production or driving deforestation. It is a testament to human ingenuity that solutions are being sought not just in new fuels, but in the very air itself, with projects exploring direct air capture of CO2 to turn into fuel. Beyond the fuel tank, the very essence of propulsion is being reimagined. Electric and hybrid electric aircraft are transitioning from conceptual drawings to test flights, particularly in the realm of smaller regional jets, and most notably urban air mobility UAM platforms. The dream of silent, emissions-free flight, powered by batteries or hydrogen fuel cells, is taking graceful form. We contemplate the silent hum of an electric motor replacing the thrum of a turbine, a profound shift that promises not only environmental benefits, but also a reduction in noise pollution around airports and cities. Yet, the energy density of batteries remains a formidable hurdle for long-haul flights, dictating range and payload limitations. This has led to intense research into advanced battery chemistries and the promising potential of hydrogen propulsion. Whether burned directly in modified jet engines or converted to electricity via fuel cells, hydrogen offers a truly zero-emission solution at the point of flight. However, the infrastructure required for hydrogen production, storage and distribution at airports presents a monumental logistical and engineering challenge, demanding a global effort akin to the development of the original jet age. Concurrently, the relentless pursuit of advanced aerodynamic refinement continues, driven by the understanding that efficiency begins with design. Every curve, every surface, every interaction with the air is being optimized with unprecedented precision, often aided by supercomputing and artificial intelligence. We see concepts like blended wing-body designs, which seamlessly integrate the fuselage into the wing, promising vastly improved lift-to-drag ratios and structural efficiency. These designs, though complex to manufacture and operate, represent a profound departure from the tube and wing configuration that has dominated aviation for decades, offering a path to significant fuel savings regardless of the power source. This holistic approach, encompassing fuel, propulsion, and airframe design, forms the bedrock of sustainable aviation, a quiet revolution promising a cleaner, calmer sky. As we gaze toward the future, another compelling vision emerges from the urban landscape, the promise of urban air mobility, UAM. Imagine a world where the frustrating crawl of ground traffic is circumvented by a network of quiet electric vertical takeoff and landing eVTOL aircraft, gracefully ferrying individuals across congested cityscapes. These air taxis, often resembling oversized drones more than traditional helicopters, represent a profound reimagining of urban transit, promising to unlock new dimensions of connectivity and efficiency. The technological advancements underpinning eVTOLs are remarkable, merging distributed electric propulsion, advanced battery technology, and sophisticated flight control systems. We observe prototypes taking to the skies, demonstrating the feasibility of vertical takeoff and landing from compact vertiports, small, elevated landing pads that could be integrated into existing urban infrastructure like rooftops or parking garages. The vision is captivating: to transform daily commutes, reduce travel times from hours to minutes, and unlock economic opportunities by connecting previously isolated urban and suburban areas. However, the realization of widespread UAM presents a tapestry of formidable challenges, extending far beyond the marvel of the aircraft itself. The sheer density of air traffic in a metropolitan area, currently managed by highly structured corridors, would need to be re-envisioned for a three-dimensional network of thousands of individual FTOLs. This demands an entirely new paradigm for air traffic management, one that is highly automated, resilient, and capable of dynamically routing aircraft, managing conflicts, and responding to unforeseen events with split-second precision. We pondered the intricate algorithms and artificial intelligence that would be required to orchestrate such a complex aerial ballet, ensuring safety and efficiency above bustling cities. Beyond the technical complexities, the integration of UAM into the urban fabric raises profound societal questions. Public acceptance is paramount. Will citizens embrace the idea of aircraft routinely flying overhead? Concerns about noise, even from quieter electric motors, will need to be addressed through careful design and designated flight paths. The visual impact of vertiports, the potential for privacy intrusion, and the perceived safety of autonomous or semi-autonomous flight will all shape public perception. Furthermore, the energy infrastructure required to support fleets of electric aircraft, charging them rapidly and efficiently, will place unprecedented demands on urban power grids, necessitating substantial investment and innovation in renewable energy sources and smart grid technologies. The dream of ascending cities is not merely about building flying machines. It is about thoughtfully redesigning the very circulatory system of our urban environments, a challenge that demands collaboration across technology, urban planning, and policy. Our journey through aviation's future inevitably leads us to contemplate the deepening symbiosis between human and machine, particularly with the advent of advanced artificial intelligence, AI. From the earliest days, pilots have relied on instruments and automation, but the AI of tomorrow represents a profound leap, promising to redefine the very essence of piloting. We observe AI's growing presence in the cockpit, evolving from sophisticated decision support systems to intelligent co-pilots capable of analyzing vast datasets in real time. Imagine an AI that can predict potential system failures before they occur, optimize flight paths for maximum efficiency and minimal turbulence, or even assist in emergency procedures with an unparalleled depth of knowledge and processing speed. This is not about replacing the human pilot, but about augmenting their capabilities, creating a highly integrated team where AI handles routine tasks and complex data analysis, freeing the human to focus on critical decision-making, unforeseen circumstances, and the nuanced art of commanding an aircraft. The ultimate frontier, however, lies in fully autonomous flight. While autonomous cargo flights are already being developed and tested, the prospect of autonomous passenger aircraft raises profound questions of trust and ethics. We ponder the shifting role of the human pilot in such a future. Will they become supervisors, remote operators, or will the cockpit as we know it fundamentally change? The ethical considerations are immense. Who is responsible in the event of an autonomous system failure? How do we design systems that are not only robust, but also capable of exercising human-like judgment in ambiguous situations? The challenge is not just to build a machine that can fly itself, but to build one that society can trust implicitly with human lives. This demands not only flawless engineering, but also rigorous testing, transparent regulatory frameworks, and a deep understanding of human psychology and acceptance. The evolution of the human-machine interface in aviation is perhaps the most captivating and complex mystery of all, inviting us to redefine the very meaning of control and responsibility in the skies. Even as we grapple with the complexities of sustainable and urban flight, the relentless human spirit continues to push the boundaries of speed and reach. The pursuit of hypersonic and suborbital flight remains a vibrant frontier, promising to shrink our world further and blur the lines between atmospheric and space travel. Imagine traversing continents in mere hours, or experiencing the sublime curvature of the Earth from the edge of space on a commercial journey. We recall the earlier aspirations for supersonic flight, and now contemplate the leap to Mach 5 and beyond. New propulsion systems like scramjets and materials capable of withstanding extreme temperatures are being developed. These technologies hold the promise of ultra-rapid global transit, transforming international commerce and personal travel. Yet the challenges are immense. The sheer energy requirements, the thermal management of aircraft skin, and the sonic boom effects on populated areas. Furthermore, the environmental footprint of such high-speed, high-altitude flight must be meticulously considered within the broader context of sustainable aviation. The dream of ultra-fast travel persists, a testament to our enduring fascination with speed, but it is a dream now tempered by a deeper awareness of our planetary responsibilities. As our journey into the future of aviation gently concludes for this evening, we are left with a profound sense of wonder at the boundless ingenuity of humanity. From the first tentative hops to the audacious visions of tomorrow, the sky remains an endless canvas for our dreams. The challenges are vast, but the dedication of those who strive to conquer them is equally immense. We invite you now to let these thoughts drift, like clouds across a peaceful sky. May the quiet contemplation of these future possibilities bring you a sense of calm and a deeper appreciation for the relentless spirit that propels us ever upward. Rest easy, knowing that the journey of flight, both physical and conceptual, continues its magnificent, inspiring trajectory. As the day gently recedes further, casting longer shadows and painting the sky with hues of twilight, we invite you to settle deeper into this quiet space we've cultivated. Our journey through the annals of aviation, from its audacious genesis to the boundless horizons of its future, continues to unfold, revealing layer upon layer of human ingenuity and unwavering aspiration. We have glimpsed the intricate dance of engineering and the relentless spirit of pioneers, and now we turn our gaze more intently towards the pathways yet to be fully charted, the challenges that beckon our collective intellect, and the quiet revolutions already taking root. The unresolved mysteries of a sustainable, accessible, and safe future for flight are not obstacles, but rather invitations to further innovation, echoing the very spirit that first lifted humanity from the earth. Our exploration of the greening of the skies is not merely a vision, it is a profound commitment, a testament to our responsibility to the very atmosphere that grants us passage. The quest for sustainable aviation is multifaceted, driven by an understanding that the future of flight must be in harmony with our planet. Sustainable aviation fuels, SAFs, offer a pathway to significantly reduce aviation's carbon footprint, with some formulations capable of cutting life cycle greenhouse gas emissions by up to 80% compared to traditional jet fuel. This is not a distant dream, but a present-day reality, with SAFs already being blended and used in commercial flights. Imagine, if you will, the serene murmur of an engine powered by fuel derived from agricultural waste, used cooking oil, or even algae. A quiet transformation occurring with every gentle liftoff. Yet, the journey to widespread adoption is complex, demanding substantial investments in production infrastructure and the development of diverse, scalable feedstocks that do not compete with food production or exacerbate land use challenges. It is a delicate balance, an intricate puzzle, demanding the thoughtful collaboration of scientists, engineers, and policymakers. Beyond these remarkable bio-derived fuels, the very essence of propulsion is being reimagined. Hydrogen, in its liquid form or as a gaseous fuel for fuel cells, holds immense promise for zero-emission flight, producing only water vapour as a byproduct when combusted or converted into electricity. Envision aircraft silently gliding through the heavens, their exhaust a whisper of pure water, leaving no trace of carbon. This vision, however, is not without its own set of profound challenges. The storage of liquid hydrogen requires extremely low temperatures and significantly larger tanks than traditional jet fuel, impacting aircraft design and necessitating entirely new airport infrastructure for refueling and handling. The quiet hum of a hydrogen-powered future is contingent upon breakthroughs in cryogenic storage and the establishment of a robust green hydrogen production ecosystem. And then there is the allure of electric flight, a concept that feels both revolutionary and in some ways a return to earlier, quieter aspirations. While battery energy density remains a significant hurdle for long-range, large-scale electric aircraft, hybrid electric systems and distributed propulsion concepts are paving the way for quieter, more efficient regional and urban air mobility. Picture a small aircraft, its wings adorned with multiple electric propellers, each contributing to lift and thrust, capable of precise control and significantly reduced noise pollution. This quote 33 approach allows for innovative aerodynamic designs, but the inherent weight of current battery technology still limits range and payload. It is a gentle reminder that every grand vision requires incremental steps, each small innovation contributing to the larger transformative whole. As we contemplate these technological shifts, we are also drawn to the evolving relationship between the human pilot and the sophisticated machines they command. The cockpit, once a realm of purely manual control, has transformed into a nexus of advanced automation and artificial intelligence, redefining the very essence of piloting. The concept of automation in flight is not new. The first truly functional autopilot system, developed by Lawrence Sperry in 1914, demonstrated its ability to keep an aircraft level and on course, freeing the pilot for other tasks. Imagine the quiet astonishment of early aviators witnessing an aircraft flying itself, a testament to Sperry's ingenuity. This early innovation, though rudimentary by today's standards, laid the foundational stone for the intricate flight management systems and automated controls that define modern aviation. It was a humble beginning to a journey that continues to push the boundaries of human-machine interaction. Today, this interaction is moving into realms previously confined to science fiction. Artificial intelligence, AI, is increasingly being integrated into aviation not to replace pilots entirely, but to serve as intelligent co-pilots, enhancing safety through predictive maintenance, optimized flight paths, and real-time decision support. envision a quiet cockpit where an AI system monitors hundreds of parameters simultaneously, predicting potential component failures before they occur, or suggesting subtle adjustments to a flight path to avoid turbulence, all while the human pilot remains the ultimate decision maker. This symbiosis promises to elevate safety and efficiency to unprecedented levels, allowing the human mind to focus on strategic oversight and complex problem solving, while the AI handles the vast torrent of data and routine tasks. Yet, this deepening integration also raises profound questions, quietly nudging us to consider the delicate balance of trust and control. The pursuit of fully autonomous flight, while technologically feasible for certain applications, involves significant ethical, regulatory, and psychological hurdles, particularly concerning public acceptance and the quote dilemma during unforeseen emergencies. Imagine a future where cargo planes or even some passenger aircraft operate without a human pilot on board, guided entirely by sophisticated algorithms. While this offers potential for reduced costs and increased efficiency, the comfort and confidence derived from knowing a human hand is ultimately at the controls remain a powerful factor. The quiet contemplation of this future requires not just technological brilliance, but also a deep understanding of human psychology and societal values. Our journey now takes us to the very fabric of our cities and beyond, to the edges of our atmosphere, as we envision new ways to navigate the world. The concept of urban air mobility, UAM, is poised to transform our daily lives, while hypersonic travel promises to shrink the globe to an astonishing degree. Urban air mobility, UAM concepts, primarily utilizing electric vertical takeoff and landing (eVTOL) aircraft, aim to revolutionize intra-city travel by offering, quote, 35, quote, services that are quieter and more efficient than traditional ground transport. Picture a quiet afternoon, and instead of navigating congested streets, you effortlessly ascend in a sleek multi-rotor eVTOL, gliding above the urban sprawl to your destination. These aircraft, designed for short-range, on-demand flights, promise to unlock a new dimension of urban connectivity. However, the path to widespread UAM is fraught with challenges. From developing entirely new air traffic management systems for dense urban airspace, to addressing concerns about noise pollution, energy grid demands, and, crucially, public acceptance and safety regulations. The quiet hum of an eVTOL in your city sky is still a future melody, requiring careful orchestration. And as we contemplate these localized revolutions, our gaze also extends far beyond, to speeds that defy imagination. Hypersonic flight, operating at Mach 5, 5 times the speed of sound or greater, relies on advanced propulsion systems like scramjet engines and novel materials capable of withstanding extreme temperatures, promising to drastically reduce global travel times. Imagine a serene morning flight from New York to London in under 2 hours, or to Sydney in less than 4. This is the promise of hypersonic travel. Scramjet engines, which compress air using the vehicle's forward motion rather than mechanical compressors, are key to achieving such speeds. However, the engineering challenges are monumental, requiring materials that can endure the intense heat generated at these velocities and precise control systems to navigate the thin, high-altitude air. It is a quiet testament to human ambition, pushing the very boundaries of what is physically possible As we journey through these grand visions, let us pause to appreciate some of the quieter, yet equally significant milestones that have shaped aviation, often overlooked but foundational to its continuous evolution. These facts remind us that progress is built not just on grand gestures but on countless acts of ingenuity and perseverance. The first successful air-to-air refueling took place in 1923 when a de Havilland DH-4B biplane transferred fuel to another, dramatically extending the range and endurance of aircraft. Imagine the delicate precision required for such a maneuver in those early days, a testament to the pilot's skill and daring. This quiet innovation, born of necessity, laid the groundwork for modern aerial refueling, a critical capability for military operations and long-range commercial flights, allowing aircraft to stay aloft for extended periods, pushing the boundaries of endurance. Consider also the essential tools that have made flight safer and more accessible. The modern flight simulator, pioneered by Edwin Link with his Quote 36 in 1929, revolutionized pilot training by providing a safe, cost-effective environment to practice complex maneuvers and emergency procedures on the ground. Picture a quiet room, a pilot immersed in a mechanical cockpit, learning the intricate dance of controls without ever leaving the earth. This humble device, born of Link's ingenuity, transformed aviation education, allowing pilots to hone their skills and build confidence in a controlled setting, significantly enhancing safety and efficiency long before taking to the actual skies. And finally, a device that has quietly safeguarded countless lives and informed every subsequent improvement in aviation safety. The black box or flight recorder, though not actually black, it's typically orange for visibility, was conceived in the 1950s to record cockpit voice communications and flight data, becoming an indispensable tool for accident investigation and improving aircraft design. Imagine the quiet, unwavering vigilance of this device, continuously capturing the story of a flight, ready to reveal its secrets should the unexpected occur. The insights gleaned from these recorders have quietly shaped every aspect of modern aircraft safety, from structural design to operational procedures, ensuring that lessons learned from every incident contribute to a safer future for all who take to the skies. As the evening deepens and the world outside softens into a gentle hush, we hope these glimpses into aviation's past, present, and future have offered you a tranquil landscape for contemplation. The story of flight is a continuous narrative of human aspiration, a gentle reminder of our capacity for wonder and our relentless pursuit of what lies beyond. May these facts settle quietly in your mind, enriching your understanding and preparing you for a peaceful rest. The quiet hum of the evening deepens, inviting us further into this gentle descent through the annals of flight. We have traversed the grand arcs of invention and transformation, witnessing the audacity that first lifted humanity from the earth and the relentless ingenuity that propelled it across oceans and into the very fabric of global connection. Our last reflections touched upon the foundational, often unseen pillars of modern aviation safety and efficiency: the meticulous black box, the immersive flight simulator, the ingenious act of air-to-air refueling. These were not mere isolated breakthroughs, but vital threads in a continuously woven tapestry, each strand reinforcing the next, leading to the remarkable reliability we experience today. As the day gently recedes and the stars begin to emerge as tiny, distant beacons, we turn our gaze towards the subtle yet profound advancements that have refined the dream of flight, making it not only possible, but also exquisitely safe, remarkably efficient, and increasingly mindful of its place in our world. These are the quiet revolutions, the incremental perfections that often go unnoticed, yet collectively define the very essence of modern air travel. From the earliest biplanes of spruce and linen, whispering tales of fragility, we have journeyed through an intricate evolution of materials, each step marked by a quiet pursuit of strength, lightness, and resilience. At the dawn of the jet age, aluminum alloys became the undisputed champions, their gleaming surfaces reflecting the promise of speed and durability. These metals, meticulously engineered for fatigue resistance and structural integrity, allowed for larger aircraft, greater speeds, and pressurized cabins that cradled passengers in comfort above the weather. Yet, the quest for perfection never truly rests. In the latter half of the 20th century, and with increasing momentum into our present day, a new family of materials began to emerge: advanced composites. Imagine materials not forged from single elements, but woven and layered like the most delicate yet robust tapestries from carbon fibers suspended in a resin matrix. These composites, such as carbon fiber reinforced polymers, CFRP, are lighter than aluminum, yet possess superior strength-to-weight ratios. They resist corrosion with an almost ethereal immunity and allow designers unprecedented freedom in shaping aerodynamic forms. The Boeing 787 Dreamliner, for instance, stands as a testament to this quiet revolution. With its airframe composed of over 50% composite materials, this shift is not merely about shedding weight. It's about crafting aircraft that are inherently more fuel-efficient, more durable, and capable of enduring the stresses of flight with newfound grace, whispering promises of a more sustainable future with every journey. The very act of flight is a delicate conversation between an aircraft and the air around it. For centuries, this conversation was largely intuitive, guided by observation and empirical testing. Early wings were often thick and relatively simple, designed primarily to generate lift. But as speeds increased and the demand for efficiency grew, the science of aerodynamics underwent a profound transformation, moving from the wind tunnel to the digital realm, allowing for an almost poetic sculpting of air itself. One of the most significant, yet often unseen, innovations lies in the development of supercritical wing designs. Unlike older airfoils that struggled with the drag-inducing shock waves created as air approached the speed of sound over their upper surfaces, supercritical wings are subtly flattened on top and more curved underneath. This ingenious shaping delays the onset of those disruptive shock waves, allowing aircraft to fly faster and higher with significantly less drag, thus consuming less fuel. Further enhancing this aerodynamic ballet are winglets, those graceful upward curving extensions at the tips of many modern wings. These elegant additions perform a critical function. They disrupt the powerful vortices of air that naturally spill from the wingtips, reducing induced drag and effectively making the wing seem longer to the air. This seemingly minor alteration can translate into significant fuel savings over long distances, a quiet testament to the continuous refinement of efficiency. Even more advanced concepts, be like laminar flow control systems, which actively manage the airflow over the wing to maintain a smooth, undisturbed boundary layer, promise even greater aerodynamic purity, further reducing drag and allowing aircraft to glide through the skies with an almost effortless efficiency. Each curve, each subtle angle, is a testament to a deep understanding of the air, a silent symphony of engineering designed to make flight ever more graceful and economical. Above us, even as the night deepens and silence enfolds, an intricate and unseen network of communication and coordination ceaselessly guides thousands of aircraft through the vastness of the sky. We have touched upon the advent of radar and basic air traffic control, but the modern ATC system is a marvel of interconnected technologies and human expertise, a silent guardian ensuring the peaceful flow of air traffic across continents. Beyond the rotating radar dishes that paint a picture of the sky, contemporary ATC relies on a sophisticated blend of automation and human intuition. Next generation air transportation system in the US and SSR, Single European Sky ATM research, in Europe are transforming this unseen weave, moving towards satellite-based navigation and surveillance. Systems like ADSB, Automatic Dependent Surveillance Broadcast, allow aircraft to broadcast their precise position, speed, and other data directly to air traffic controllers and other aircraft, offering a more accurate and comprehensive picture of the airspace than traditional radar alone. This enhances safety, particularly in remote areas or at lower altitudes, and allows for more direct, fuel-efficient routes. Furthermore, collaborative decision-making platforms enable airlines, airports, and ATC to share real-time information, optimizing flight plans and ground movements to minimize delays and maximize efficiency. Imagine a delicate, synchronized dance where every participant is aware of the other's movements and intentions, orchestrated by an unseen hand of technology and human oversight. This constant refinement of air traffic management ensures that the skies, despite their increasing density, remain a peaceful and orderly domain, guiding each journey with quiet precision from departure to a gentle arrival. While technology undeniably propels aviation forward, the human element remains at its very heart. Early aviation often celebrated the lone, heroic pilot, a figure of audacious courage. However, as aircraft grew more complex and the environment more demanding, it became clear that individual brilliance alone was not enough to guarantee safety. This realization gave birth to one of aviation's most profound and enduring safety innovations: Crew Resource Management, CRM. CRM, developed in the late 1970s and early 1980s, shifted the focus from individual pilot skills to the effective utilization of all available resources, human hardware and information, within the flight deck and cabin. It's a philosophy centered on fostering clear communication, assertive yet respectful leadership, mutual support, and effective decision-making under pressure. Pilots, flight attendants, and even ground crews are trained not just in technical skills, but in the softer yet equally critical arts of teamwork, conflict resolution, and stress management. Imagine a cockpit where every voice is heard, every concern is respectfully considered, and every decision is a product of collective intelligence rather than singular authority. CRM transformed the culture of the flight deck, moving away from rigid hierarchies to a more collaborative environment where errors could be identified and mitigated before they escalated. This quiet revolution in human interaction has saved countless lives, proving that even in the most technologically advanced machines, the harmonious synergy of human minds remains the ultimate safeguard, ensuring a calm and confident journey for all. The intricate dance between human pilot and machine has evolved dramatically, moving from direct mechanical linkages to sophisticated electronic control. This transformation, often unseen by the passenger, has brought unparalleled precision, stability, and safety to modern flight. We speak of a fly-by-wire FBW systems, a quiet revolution that replaced heavy, complex mechanical cables and pulleys with electronic signals. In a fly-by-wire aircraft, the pilot's control inputs are no longer directly transmitted to the control surfaces, like ailerons, elevators, and rudder. Instead, a computer interprets these inputs, then sends electronic commands to actuators that move the control surfaces. This allows the flight control computers to constantly monitor and adjust the aircraft's attitude, providing stability augmentation and making the aircraft inherently easier and smoother to fly. But the true genius of FBW extends beyond mere convenience. These systems incorporate envelope protection, a crucial safety feature. Imagine an invisible barrier around the aircraft's safe operating limits, its maximum speed, angle of attack, and bank angle. The fly-by-wire system, acting as an intelligent co-pilot, can prevent the aircraft from exceeding these limits, even if the pilot inadvertently attempts to do so. This quiet intervention safeguards against stalls, overspeeds, and structural overstress, adding an extraordinary layer of protection. It allows pilots to focus on strategic decision-making while the aircraft gracefully manages its own stability, ensuring a consistently calm and controlled flight experience. In the relentless pursuit of perfection, modern aviation has embraced the power of data and foresight, moving beyond reactive repairs to a proactive approach that anticipates needs before they arise. This is the realm of predictive maintenance, a silent sentinel constantly monitoring the health of every aircraft component. Imagine thousands of sensors embedded throughout an aircraft, from its engines to its landing gear, constantly gathering data on performance, temperature, vibration, and countless other parameters. This deluge of information is then fed into sophisticated algorithms and artificial intelligence systems. These systems learn the normal operating signatures of each component, identifying subtle deviations that might indicate an impending issue long before it becomes a problem. Instead of waiting for a part to fail, maintenance crews can schedule replacements or repairs precisely when they are needed, minimizing downtime, reducing costs, and, most importantly, enhancing safety. Further extending this foresight are digital twins, GIM. Envision a virtual exact replica of a physical aircraft, constantly updated with real-time data from its real-world counterpart. Engineers can use this digital twin to simulate various scenarios, test modifications, predict wear and tear, and even anticipate the effects of environmental conditions. This ability to model and predict the future behavior of complex systems allows for optimized maintenance schedules, more efficient operations, and an unprecedented level of understanding of an aircraft's lifespan. It's a quiet revolution in operational intelligence, ensuring that every flight is undertaken with the utmost confidence in the reliability and integrity of the machine. As air travel became an integral part of global life, the harmonious hum of engines sometimes brought with it a less welcome companion: noise, Communities surrounding airports in particular felt the impact. In response, the aviation industry embarked on a quiet yet determined mission to reduce its acoustic footprint, striving for a future where the wonder of flight could coexist even more peacefully with daily life. This commitment to quietude has manifested in myriad ways. Engine manufacturers have invested heavily in designing quieter turbofan engines, incorporating larger fan diameters, advanced acoustic liners within the engine nacelles, and more sophisticated airflow management systems. These innovations significantly reduce both the high-pitched whine of the compressor and the low-frequency rumble of the exhaust. Beyond the engines, aerodynamic refinements play a crucial role. Aircraft designers meticulously sculpt the wing and fuselage to minimize aerodynamic noise generated by air flowing for surfaces, particularly during approach and landing. Even the landing gear, when deployed, can generate considerable noise, leading to designs that are more streamlined and retract more quickly. Furthermore, operational procedures such as optimized descent profiles, continuous descent approaches or CDAs, that allow aircraft to glide down more quietly with less engine thrust, contribute significantly to reducing noise pollution around airports. It is a testament to the industry's evolving responsibility, a gentle whisper of progress ensuring that the marvel of flight can continue to inspire without disturbing the tranquility below. The vastness of the skies, untamed by national borders, necessitates a shared understanding and a collective commitment to safety. From the very early days, it became evident that for aviation to truly flourish as a global connector, nations would need to speak a common language of flight. This realization led to one of aviation's most significant, yet often unseen, achievements: international cooperation and standardization. At the heart of this global embrace lies the International Civil Aviation Organization, CAO, a specialized agency of the United Nations established in 1944. ICAO's mandate is to develop international standards and recommended practices, SARPs, concerning air navigation, the infrastructure of airports, air traffic services, the licensing of personnel, aircraft design and manufacturing, and environmental protection. Imagine a harmonized set of rules and guidelines that every signatory nation agrees to uphold, creating a seamless and predictable operational environment across the entire globe. This standardization ensures that a pilot licensed in one country can fly an aircraft registered in another, following air traffic control procedures understood by controllers of a third. It means that aircraft parts manufactured in different nations conform to the same rigorous quality and safety specifications. From the symbols on airport signs to the precise procedures for an emergency landing, ICAO's quiet work underpins the entire global aviation system, fostering an unparalleled level of safety, efficiency, and trust. It is this silent agreement that allows us to embark on journeys across continents with a calm assurance, knowing that the principles guiding our flight are universally understood and meticulously observed, weaving a peaceful network across the world's diverse tapestry. As our gentle journey through these facts continues, we're reminded that aviation is not merely a story of grand inventions, but also a continuous narrative of refinement, adaptation, and an unwavering commitment to improvement. Each quiet innovation, each deliberate step, adds another layer of wonder to this incredible human endeavor, inviting you to rest in the knowledge of its enduring safety and grace.